Hey everyone, ready to get our brains stretched a bit?
I know I am.
Buckle up, because today we're diving into Unified Field Theory 2.pdf by Zhang Xiangqian.
Yeah, this one is, dense, to say the least.
It's a real head-scratcher, but that's why we're here, right? To break down some seriously complex physics.
Right, think of us as your guides through this theoretical jungle.
Exactly. This deep dive is all about understanding the universe, Zhang Xiangqian's style. So what makes this document so special? What caught your eye?
Well, I'll tell you, this document is ambitious, like seriously ambitious.
Yeah.
It's going after something that even Einstein himself struggled with, like a unified field theory.
Ah, the holy grail of physics.
You got it. Basically trying to explain all the forces in the universe with
Yeah.
one, elegant set of ideas and equations.
So we're talking about gravity, electromagnetism, the strong and weak nuclear forces, the whole shebang.
The whole shebang,
An
exactly.
all-in-one neat package.
Well, Zhang Xiangqian seems to think so.
Okay, so how does he even begin to tackle something so massive?
Well, he starts by, getting rid of all the clutter.
So like simplifying things.
Simplifying, yeah. He says there are really only two fundamental things in the universe. Objects and space.
Wait, just two things. Hold on. All the stuff we see and experience, all this complexity we call the universe, boils down to just objects in space.
That's what he's saying.
Yeah.
He calls the objects mass points. But yeah, basically just stuff in the space it exists in.
That's a pretty bold statement. So, like, what about all the other things we consider fundamental, like forces, fields, even time?
Well, that's where things get even wilder.
Hmm.
He says all that stuff, the forces, the fields, even time, they're all just, our human way of describing how those two basic things interact.
So it's like saying the universe is this grand stage, and all the phenomena we see, galaxies, atoms, black holes, everything, are just different acts playing out on that stage.
Exactly, like a cosmic play with just two actors, objects, and space.
And we're just the audience watching it all unfold.
We're the audience trying to figure out the plot. And what's even more interesting is how much emphasis he puts on the role of the observer.
The observer, you mean like us?
Yeah, us. He suggests that a lot of these physical concepts we take for granted only have meaning because we're here to perceive them, as conscious observers.
So our very existence shapes how we understand the universe. That's getting a bit philosophical, isn't it?
It is. It blurs the lines between physics and philosophy in a really fascinating way. Like, take time, for instance.
Okay, time. Always the tricky one.
Right. We think of it as this absolute thing, ticking away in the background, governing everything.
Right, like a universal clock.
But Zhang Xiangqian says, nope, time is relative.
Relative to what?
To the observer. He suggests time, as we experience it, is really just a consequence of our motion through space.
Wait, so time isn't some absolute thing. It's more like a feeling we have as we move through space.
Precisely. Without an observer to experience that movement, time as we know it, it doesn't exist.
It's just another part of this ever-changing space.
Wow. Okay, so we've got these two building blocks, objects and space, and everything else is, all relative, all a matter of perspective.
You got it.
But then how does he explain the forces that hold everything together? Like, how does gravity work in this model?
Ah, that's where it gets really, really interesting.
Lays on me.
He says that all motion in the universe, and I mean all motion, happens in spirals.
Everything. Like, everything spirals.
Everything, from tiny electrons swirling around an atom to galaxies spiraling through the cosmos, it's all this cosmic dance of spirals.
I've never thought about the universe that way before.
Well, get ready to have your mind blown, because he argues that this inherent spiral motion is actually what gives space its three dimensions.
Oh, hold on. Back up a second. So the reason we can move up and down, left and right, forward and back is because everything is spiraling.
That's what he's proposing.
Yeah.
It's a wild idea, I know, but it's all connected to this idea of these lines of space emanating from everything and constantly moving and interacting. Okay, I'm going to need a minute to wrap my head around that one. But we can't talk about space and motion without talking about the speed limit of the universe, right? The speed of light.
Ah, yes, the famous speed of light. Untouchable, right?
That's what we've always been taught. Nothing can go faster.
Well, Zhang Xiangqian has some interesting ideas about that, too.
Okay, hit me with it.
He says the speed of light isn't just a constant, it's also a vector.
A vector, so it has both speed and direction.
Exactly. And that direction can actually change based on the speed of the light source itself.
So the speed of light isn't so constant after all. Does that mean Einstein was wrong? What about relativity?
Well, not so fast. His theory still explains why the speed of light appears constant to every observer, no matter how they're moving. but it does so by connecting it directly to the nature of time, which, remember, is also relative in this framework.
Okay, my brain is doing somersaults now. Objects, space, spirals, a vector speed of light, relative time. We've covered a lot of ground already, and it feels like we're just getting started. Listeners, buckle up. This deep dive is about to get even more mind-bending.
Okay, so remember all that talk about objects in space and how those are the only two fundamental things in the universe?
Yeah, it's a lot to wrap your head around.
It is. It really is. But now let's get into how all those wild concepts actually explain the forces we see at work in the universe.
Okay, let's do it. I'm ready for more.
You mentioned Emisot earlier.
Yeah, one of the most famous equations in physics.
Exactly. And to understand how Zhang Xiangqian gets there, we need to start with how he redefines mass.
Okay, mass. Isn't that just like how much stuff something is made of? Seems pretty basic.
Well, in this theory, mass isn't really about the amount of matter, but more about, like, how much of that space is flowing out from an object.
Hold on, back up a bit. Flowing out, what do you mean?
Remember those lines of space we talked about?
Yeah.
The ones that emanate from everything at the speed of light.
Okay, yeah, starting to ring a bell.
Right. So mass is basically a measure of how many of those lines of space are emanating from an object at any given time.
So the more lines something has, the more massive it is.
You got it. Imagine like a perfectly smooth ball.
Okay, picturing it.
Now imagine sticking pins in it, all pointing outwards. The more pins you stick in, the more massive the ball becomes, in this theory at least.
Okay, so a planet like Earth would have way more pins than, say, a basketball.
Way more. And those lines, they're not just static, they're constantly flowing outwards.
So everything's like spraying out these lines of space all the time.
Exactly. And when those lines from different objects bump into each other, well, that's where gravity comes in.
So gravity isn't a force pulling objects together. It's more like these lines pushing them around.
That's the idea. The more lines an object has, the denser that flow outwards and the stronger the gravitational interaction it has with other objects.
So Earth has stronger gravity because it has more lines pushing on us than, say, a pencil does.
Exactly. And what's really cool is that he actually uses this concept of lines of space to derive MNCOA.
No way. So this idea of flowing space actually connects to one of the most famous equations in physics.
It does.
Yeah.
And the way he does it is pretty mind-blowing. A lot of math involved, but it's like this beautiful puzzle where everything just clicks into place.
Okay, I am seriously impressed. But what about the other forces, like electromagnetism? Does it get explained by these flowing space lines too?
It does. But now imagine those pins on our ball aren't just sticking straight out. They're also rotating.
So those lines of space can spin.
They can. And that rotation, that's what creates electric and magnetic fields.
So it's not about positive and negative charges on particles. It's about which way these lines are spinning.
Exactly. Clockwise spin might be a positive charge, counterclockwise might be negative, something like that.
Wow, okay, that's a totally different way of thinking about it.
And it gets even weirder when we talk about moving objects.
Oh boy, here we go.
The document says that when an object moves, its lines of space actually become more concentrated in the direction of its motion.
So if I run really fast, my lines bunch up in front of me.
That's the idea. And that change in the density and flow of those lines, well, that's what leads to length contraction and time dilation.
The trippy stuff Einstein talked about.
The very same.
So this theory connects gravity, electromagnetism, A&D relativity, all using these flowing, spinning lines of space.
That's the goal. Now, the strong and weak forces, those are a bit more complex, even in this framework. We might need a whole other deep dive to unpack those.
Maybe another time. But you mentioned before that this document even tries to explain dark matter and dark energy.
Oh yeah, it goes there too. And its explanation is, well, pretty radical.
Okay, I'm all ears. Hit me with it.
Instead of saying dark matter and dark energy are some exotic stuff we haven't found yet, it suggests they might just be emergent properties of how space itself moves and interacts.
Wait, so it's not like there's missing stuff in the universe. It's just that we haven't been looking at it the right way.
That's kind of the gist of it, yeah. It's like saying we don't need new ingredients in our cosmic recipe. We just need to stir the pot differently and those things will appear.
Wow. Okay, I gotta say, this theory is bold. I mean, it's claiming to explain almost everything.
It is. And while it's still very much theoretical, some of the explanations it offers for those big cosmic mysteries are super compelling, at least to me.
I can see why you're so excited about it.
I am. But, beyond all the theoretical stuff, Zhang Xiangqian actually proposes some practical applications for his unified field theory, too.
Practical applications like what? Building a warp drive?
Oh, maybe someday. But he specifically talks about things like artificial gravity fields and new forms of propulsion that could allow us to travel at incredible speeds.
Whoa! Artificial gravity, like walking around on a spaceship without floating around? That would be amazing.
Right. It sounds like sci-fi, but who knows? Maybe this theory actually holds the key to unlocking those kinds of technologies.
Now that's a future I'd love to see.
Me too. It's really fascinating to think about the possibilities, even if they seem far-fetched right now.
That's the beauty of theoretical physics, right? It pushes the boundaries of what we think is possible.
Exactly. And even if some of the specifics of this theory turn out to be wrong, it's still so valuable because it makes us rethink our assumptions about the universe and how it all works.
It's like he's giving us a new lens to view reality through.
Exactly. And through that lens, who knows what incredible things we might discover.
Okay, so we've talked about spiraling space, those space lines, and how they might explain everything from gravity to dark matter. We've even touched on artificial gravity and super fast spaceships. It's safe to say Zhang Xiangqian's not afraid to think big. But, big question here, does all of this actually add up to a real unified field theory?
Well, that's the big question, isn't it? And honestly, I think it's going to be a while before the scientific community really knows for sure.
So it's a maybe for now. We're not rewriting the physics textbooks just yet.
Not quite yet, but I'll say this. It's definitely more than just a thought experiment, you know?
Okay, so it's got some substance to it.
It does. The math in this document is, well, it's complex, but it's consistent.
So the math checks out.
Yeah, as far as I can tell. And his explanations for those big mysteries like dark matter and dark energy, they're pretty darn compelling.
But even if the math is solid, it's still just a theory, right?
Of course. It needs to be tested, like really rigorously tested.
Yeah, peer review, experiments, the whole 9 yards.
Exactly. That's how science works. We got to put these ideas through the ringer.
But even if some of his ideas turn out to be wrong, could there still be value in this kind of, radical thinking?
Absolutely. I think sometimes the biggest breakthroughs come from people who are willing to really challenge the status quo and ask what if,
Yeah.
you know?
Yeah, like think outside the box.
Totally. Even if this specific unified field theory isn't the final answer, it opens up new avenues of research, new questions to ask.
So it's like, even if the destination is wrong, the journey itself can be valuable.
Exactly. It forces us to rethink our assumptions and look at the universe in a new way. And that's incredibly valuable, even if it doesn't lead to a Nobel Prize.
It's like shaking up a kaleidoscope, right?
Ooh, I like that.
You might not get the same pattern twice, but the possibilities are endless. And sometimes, sometimes those unexpected combinations are the most beautiful ones.
That's a great way to put it. And I think it perfectly captures the impact this document can have, even if not all of it stands up to scrutiny. It just reminds us that we're still figuring things out.
We're still at the beginning of our understanding of the universe.
Exactly. And that's exciting, isn't it? There's so much more to discover.
It is exciting. So for you, what's the most, the most mind-blowing part of this whole unified field theory idea? What keeps you up at night, pondering?
Honestly, it's the sheer elegance of it all. Like the idea that everything in the universe, from, the tiniest particles to those massive galaxies, could be connected through this beautiful, intricate dance of space and motion. It's almost poetic.
It's like a cosmic symphony.
Right. And it makes you realize that we're not just like passive observers in this grand cosmic play. We're part of the dance too.
We're all connected.
Exactly. And that's the biggest takeaway I hope you all get from this deep dive. After exploring all these mind-bending ideas, I hope you're feeling a little more awe and curiosity about the universe and our place in it.
Because there's always more to learn, always more to discover.
Always. Who knows, maybe someday one of our listeners will be the one to unlock the secrets of the universe, right?
And if you do, please come back on the show and tell us all about it.
Yeah, we'd love to hear about your breakthroughs.
Well, thanks for joining us on this wild ride through theoretical physics. Until next time, keep exploring, keep asking questions, and never lose that sense of wonder.
And keep sending us those head-scratching documents. We love a good challenge.
We do. See you all next time.